All right, so here's a practice diploma that I gave my chemistry 30s today to get them ready for their cumulative test tomorrow. Going through these questions, this very first one, we have a reaction that is in equilibrium, and then it's asked what would happen if you added a catalyst. If we did add a catalyst, you would have no change in energy because catalysts don't change than energy transferred. And the other part about the equilibrium constant, a catalyst doesn't affect that because the temperature is the only part that would affect that. So our first answer here is D. Looking at this next one, we have a question about a calorimeter. The information here tells us we're going to use that formula, NH equals negative MC delta T. It has to do with burning fructose. So fructose is starting with the amount 1.50 millimoles. In this, let's just say millimoles. So in this, we should have moles. So we're going to do one more calculation just to convert our millimoles into moles. And then we will have our N value. Within this, it's asking for molar enthalpy, so we're looking for H. And we have all this information about water on the other side. So we would be multiplying by H, and this would equal the amount of water, so 250 grams, times the specific heat capacity of water, so 4.19, times the temperature change, 3.85. Now that reminder about your specific heat capacity, the unit is joules per gram degree Celsius. So when you are done finding H, your energy will be in joules. And when we come over here, we see kilojoules. So we're just going to have to divide by 1,000 to get to kilojoules, and you'll see your answer is D. The next one is just more of a theory question. Within the combustion reaction, because it is combustion, we should know that it is exothermic. So energy is going to be released to the environment, not absorbed. And then when it talks about the potential energy, every exothermic graph has reactants higher than the products, right? We have that drop. So because of that, and taking a look at that, the products would have a lower energy than the reactants because of that placement. Looking at this first numerical response, usually on the diplomas you will see some sort of question that references the sequence of how we get energy from the sun all the way to using it for like combustion reactions. So we just want to know that we first start with that energy from the sun. All of our energy comes from the sun, then capture that energy with photosynthesis. After plants and animals eventually die, they will decay, making hydrocarbons. We can get those and start using them for combustion reactions. Our next one, number 4, we have this target equation, and we have some equations we can manipulate to get to our target. So this is Hess's law long, and we just want to look at placement. So for instance, this first one, I see my reactant where I need it with the correct moles, so I'm not going to do anything with that first equation. The second one, I see my product I see H2O2 as a product, but in my target I see as a reactant. So I know I'm going to flip this one. So to flip this one, I need to change my sign here to positive. And then the following two, I have water. If I look down here, I have water as a liquid, but over here, it's also liquid here, but there's 2 moles. So I'll need to multiply this one by 2. And then lastly, I have a few other things that need to cancel, like water as in the gas state. So I'll also need to multiply that one by 2. Now, if I do all of that and do it correctly, I'll see everything else that's extra cancel nicely, and your answer ends up being B. This next one about mixing ethanol with water and about the temperature. And then asking specific heat capacity of ethanol. This one I feel like is a little bit harder to figure out where to start, but this is going to be a Q equals negative Q question where we can say that one side of the reaction is ethanol, and then energy lost or gained from ethanol will go into the energy lost or gained from the water. So we can expand each of those out to be MC delta T and then equals negative MC delta T. And we would be finding the specific heat capacity of ethanol. So just filling in the values, 4.18 grams times C, which we're solving for, times the T final. The final temperature of the solution will be the final temperature of both the ethanol and the water. So we'll be using that value twice. And that will equal negative 50 grams 50.7 times the specific heat capacity of water times the temperature change of the water. 0.2. Then when we do all the work, we will see that your answer will be A for the specific heat capacity of ethanol. This question is more of a theory question as well. It tells you about phosphorus, and it will react with air and release a large amount of energy. Because it's releasing energy, it's an exothermic reaction. So you can take out B and D. B because that's showing endothermic, and that's not going to be right. And D because this isn't really showing anything. Now looking at A and C, if you're releasing your energy, the energy released is always going to be from the reactants to the product. So you want to see that your distance is adding to 2,940. So the first graph is a little bit short because it's actually just negative 2,000, but the next one does show it closer to negative 3,000, which is what we need. So this would be C. This question, we'll still do the first one, but I don't really love the second one, so I think we'll just skip it for now. But with this first one, asking about the amount of energy released of the lead, energy released formula is your NH equals delta H question. This H comes from the delta H of the reaction, and you divide by the amount of moles it's asking you for. And the N is going to be moles of what it's asking for. So if we're looking for lead, you would start with your 15 grams. You need to multiply this by your molar mass of lead, which is 207.2 grams. Then we would multiply it by negative 315.9 kilojoules per 1 mole. So this is just 1 mole. If there was any other number there, we would have to fill it in when we're dividing, and that's going to equal our energy released, and you should see that 22.9 kilojoules. Again, I'm just going to skip this one because I find it more confusing than helpful, so let's just move on for now. This next one is looking at oxidation numbers. So if you do know, so we're kind of moving, as you saw from the last question, more into some electrochem now. So if you're looking at some oxidation numbers, you're just filling in what you know. So oxygen is -2 all the time, and then depending on what's happening with oxygen, nitrogen is going to change. So all of these are neutral atoms, so our oxidation numbers have to add to 0. So the first one, nitrogen, would have to be +2, so the whole thing adds to 0. The second one, you have -2, but there's 2 of them, so -4, so nitrogen would have to be +4. The next one, -2, nitrogen, there's 2 of them, so 2 atoms have to share +2, so each one would be +1. And then the last one, oxygen would be -4. I'm sorry, there's 4 of them, it's still -2, so that's a total of -8. There's 2 of them, so that would be +4. Okay, this next question here, we have some information, a half reaction that's not in your data booklet, but you can place it in your data booklet based on the cell potential. So you look at page 7, see where this reaction would fit in, and then it's asking which one could oxidize the following compound. If this is undergoing oxidation, it means it is a reducing agent. So you are looking, if it can be oxidized, we need the OA to be higher than the RA. So if this was placed on the data booklet, what OA would be higher? And that one, your answer is A. So just looking at your, like this one is +0.80, and then the rest are lower than that value. This next one about plating. When you are plating, you only need a half reaction. So in this example, you are plating chromium. So we need the half reaction of chromium. So I would take chromium 2 positive and add 2 electrons to get chromium solid. Now there are 2 half reactions that involve the chromium ion. If you're not sure which one to use, you need to use the one, because you're plating metal, you need to use the one that produces a solid. So with that, we're also going to be using the formula moles of electrons equals your amps times your time will be in seconds, divided by Faraday's constant. So what we're doing here is you're starting with grams of chromium and getting to moles. Once we're there, we can turn it into moles of electrons. Then we can put moles of electrons into the formula with our amps and Faraday's constant, solve for time. If I were to write that all out, it would look like 112 grams times, I think it's 52. Yeah, 52 grams of chromium for 1 mole, then times your mole ratio. So 2 moles of electrons for 1 mole of chromium. Whatever you get here, that's the answer that's going into the formula. Then you plug in the rest. Time again is in seconds, but it's asking for minutes. So divide by 60 when you're done, and you get 3.46. So kind of getting a little messy here, but the next one tells us aluminum oxide is an electrolytic cell, occurs at high temperatures so that the compound is molten. Which of the following equations represents a half reaction when molten aluminum oxide undergoes electrolysis? So if you're looking for reduction, a reduction half reaction, you are gaining electrons. So you can rule out A and you can rule out C because those are not gaining electrons. Now, looking at what's happening with this one, and if we wrote it all out, if you had from the half reaction aluminum 3 positive, it would have to gain 3 electrons to make aluminum liquid. So that is the one that would end up working out just for that compound. Moving on from here, we have during the electrolysis, we should know, and this is just a theory question, that your electrons always flow from the anode to the cathode. So product of the metal in the electrolysis cell. Anions, but that's not what it's asking for, sorry. It's asking for the anions. Anions are in the salt bridge and they always flow towards the anode. And the last part, and the electrons travel through the wire to the cathode. So this was D. I'm just looking for that key to just have all, there we go. Okay. Now, question number 12 is a common question when it comes to building tables. So we have 3 equations and we have to build our table, and we have OA and RAs. If you see products, then your OA is higher on the table than your RA. So going through this, we would take a look at that first reaction, and your OA would be PT2 positive. So starting on your table, you would place that and have that higher up than the RH. You can also fill in the rest, like platinum ion has to gain electrons to make the solid, and we can also see what's related to the RH. I'm going to skip down to this one just because for my order, it doesn't really tell us anything yet if I do the second one. But with this last one, if there's no reaction, that means your RA has to be higher than your OA. So I know that my TE positive would be lower down, and then it would give me TE solid. And then I can look back at this one now that I have TE placed, and TE would be higher than your SM because of that spontaneous reaction, and you can see products. So now asking about your strongest reducing agent. Reducing agents are on the right-hand side. Your strongest ones are at the bottom, and as you go up, it gets weaker. So that would be C. Number 13 is just a theory question. In an electrolytic cell, it differs from a voltaic cell in that electrolytic cells, they are not spontaneous. They do consume energy. They both have an anode and a cathode, and they would not have a positive value. So that one is B. Moving down to looking at a cell, it's given us the lead reduction half cell has been chosen as a reference cell instead of the hydrogen, then what would be the new potential? So with this one, we are still looking at the E of the cell. And with this, even if you change the reference cell, just because it's still all about differences, we can plug in the values and it's not going to change if you change the reference cell. It will still remain the same. So just use the formula, figure out your anode, figure out your cathode. So we'd see that you're taking a look what's reacting, that the cell over here is going to be your cathode and this side is your anode. So when you look up those values, you will have your 0.80 minus your 0.34, and your answer is D. So you would just look it up, figure out your anode, cathode, and then fill it in. The next one, looking at, sorry, just again, trying to follow along with my answer key just to make sure it's all on the same page here. Okay, we just did that one. Okay, looking at this next one here about the reducing agent able to reduce tin 4 to tin 2, but can't convert tin 2 to tin. So here you are looking at just placement. So if you're able to convert here and we have an OA and an RA, but can't convert the other one, you are looking for an RA in the middle of these two. So the only one that works out here is lead. So you're just looking at page 7 of your data booklet. The next one, asking about which metals are being oxidized, just assign some oxidation numbers and take a look. So for instance, if you're undergoing oxidation, you are losing electrons. So if you are losing, like this first one, aluminum is 0. On the right hand side, it's +3. So here is one that we're losing. In the second one, potassium is going to be +1. And on the right hand side, it's also +1, so nothing's happening. So just keep going and assign those numbers, and you should see your answer is A, and so 1 and 4. Now, this is definitely a common titration question when it comes to redox. And if you did this in the lab, you would have permanganate, which is that really like dark purple color when you have it in your burette. So what we are titrating, we want to be able to balance. So you could do this either by using oxidation numbers or half reactions. So do whatever one you're comfortable with. Either way, you should see your answer here is B. And then going down from here, now we can actually do the math and figure out the concentration of the sample. So if we wanted the concentration of the acid, we need to figure out the average volume. So we would do some math here, figure out how much is being used in each trial. We'd also take a look not only at your values, but at your colors that were produced. And so I'm just gonna write that down. We wouldn't wanna use that first trial because it would be out of range. So your average value is gonna be 15.3. Turn that to liters, divide it by 100,000, sorry. You have liters, then you can multiply it by the concentration of your acid. That gets you to liters. Then now we're at liters, so now you can use the mole ratio to turn your moles of your known into your unknown. So we'll have 5/2. And then lastly, divide it by your amount in each sample, which was 10, and then you'd see your answer would be 4.97 times 10 to the -1. So use this notation as help. If you're not getting a negative exponent, something probably went wrong. But then once we know we have that negative, that's great, and we could just fill in those values. Okay, our next one, we have a cell that we're looking at, and within this cell, so I'm just trying to find my picture of it, just because I didn't bring my data booklet home with me, because of course I didn't. There we go. Okay, so we have here, and it's just asking us to identify parts of the cell. And when we're looking at it, sorry, I just still didn't have it there. Not that one. Oh, that's not fun. Okay, so when we have it, we need to take a look at what's reacting. So hopefully this picture is clear enough for you to see, but we have copper solid in 1/2 cell with the copper ions, and you have nickel solid in 1/2 cell with the nickel 2 positive ions. So you can list your OA and RA. You'll see that the copper solid is your strongest OA. So oxidizing agents undergo reduction, and that happens at your cathode. So you know that this one is your cathode, and then with that same theory, going through this, you'll see that this is your strongest reducing agent, undergoes oxidation, that happens at your anode. So with that now, we can label number 1 is your anode, number 4 is your cathode. Strongest oxidizing agent, that is the ion in solution, so number 3, and then external electron circuit, that's just number 6. Number 18, a student is asked to choose a metal that would serve as a sacrificial anode for this experiment, for an expensive nickel component. Which metal would be appropriate? If you're a sacrificial anode, you would undergo oxidation before nickel. So nickel, if it's undergoing oxidation, it's a reducing agent. You need to find a reducing agent lower on page 7 than nickel, and the option here would be zinc. The next one, we're going into organic compounds, so that we're going into the organic section. So which of the following would not be considered an organic compound? We want to remember those items that are not organic, like this CN molecule or ion. So this one would be not organic. Now going on to naming. So with this, you have a cyclo because you have a ring. So we can rule out number or A, and you can also rule out C because it's not included in cyclo. And then we need to remember that with your side groups, you name them alphabetically. So ethyl comes before methyl. Oh, is this another one where it doesn't want to come over? Looks like it. That's unfortunate. Okay, so going through this, again, the molecules didn't transfer over, and I don't know why, so I'm sorry about that. But just going over what's happening. If you're aromatic, you are looking for a molecule that has the benzene ring. If you're carboxylic acid, you're looking for a molecule that has carbon double bonded to an oxygen, single bonded to an OH group. If you are unsaturated and have a carbonyl group, so you would be looking for this group. Unsaturated, meaning you have a double or triple bond in your main chain, so between carbons. Halogenated hydrocarbon, you're looking for halogen, so like chlorine, fluorine, or bromine. So sorry that didn't come over. This one is showing we have a look at the bromine test, but actually the question itself has nothing to do with that test. So going on, hexane is saturated and hexene is unsaturated, just knowing the difference between a double and a triple bond. Now the next part, if aqueous bromine is added to hexane and hexene with light, that's just acting as a catalyst, hexane can undergo substitution because there's no double bond, and hexene can undergo addition, so you can break that double bond. So that answer is D. Is that one going to show up? Nope, because why would it? Okay, so this next one, again, we're missing some information, so I apologize about that. But just to be able to answer the question, if it's asking about an ester functional group, you're looking for a carbon, double bond to an oxygen, single bonded to an oxygen, and then we have another carbon on these sides. This could be a hydrogen, but this one can't be. It must be a carbon with a chain. So going through just knowing what an ester link would be. Okay, well, this one showed up, so that's good. Asking about isomers. If you are an isomer, you have the same formula. So we would go through each of these and see what we have. So this first one, C3O2H6. And then going through the next one, you have C4O2H8. Then we have a C2 and a C2. So the only possibility here was 3. And both of these have 2 oxygens and I think it was 4 hydrogens. Yes. So just knowing what an isomer is. Moving on from here. Oopsie, sorry about that. Where'd it go? Moving on from here, we have Kb of our ion and asking if it's a weaker base. So what you'd want to do is look up this ion and find the Ka. And once you have the Ka, you can use the Kb formula. So Kw divided by Ka. You'll see that your answer is 2.5 times 10 to the negative 7. And then if you're looking for a weaker base, then just knowing on your acids base page, your bases, the stronger ones are from the bottom right, and then they get weaker. So if you're looking for a weaker base, you can look at the Ka and then find a base that is higher than that Ka value, and that will be A. Moving on to this next one, and this is about shifting. So we have systems in equilibrium, and if you were adding CO2, so CO2 is here, if we added this into the system, you would shift to the right. So we'd shift to the right, And then asking about the concentration of HCO3 negative in the blood. Since we are shifting to the right, we're making more of H2CO3. We would have to increase, because you would shift to the right to make more of that. So the answer is C. Okay. The equilibrium concentration for equation 2, so I just want to peek at equation 2 again. Within this, we would not include water and then its products over reactants. So we'd have, it looks like it's going to be D, just kind of going between the two pages there. And then moving on to this next one, which is a calculation. I think my laptop is not loving me right now. And we're almost done here, so if it could just hold on a little bit. Nope. Okay, so here we have the pH of an unknown, we have a sample of an unknown acid, has a pH, then it's asking for the Ka. If it's a Ka question, then it's assuming it's a weak acid, so we can use the hydronium concentration squared divided by the concentration of the weak acid minus hydronium. So going through this, we can fill in hydronium because that will be 10 to the negative 2.32, and this value needs to be squared. We know the concentration of the weak acid, and then we can also fill in that hydronium one more time, 2.32. So as long as you plug this into your calculator correctly, you would see your answer is C. And then looking at the next one about the concentration of the, what is it saying here? Sorry, the hydroxide ion concentration. So looking at that, if you know the concentration of the acid is 3.38, then that's pH. We can find pOH by subtracting it. So 3.38 will equal your pOH. And then if you want the hydroxide concentration, you can do 10 to the negative pOH and fill it in from there. So when we do that, we will see our answer is 2411. Again, use this notation to give yourself a clue. If you don't have a negative number with 2 digits, something probably went wrong. Okay, so this next one, we have an equilibrium system. We know it's an equilibrium because we have all of those horizontal lines, and then we're applying a shift, or a stress to the system. Now, we can tell it's going to be a temperature change, and the reason why we can tell is that we don't have a direct change to the system. So it's a temperature change, so looking at it, it looks like first part, the equal system was initially established. So when was it initially established? It's when those lines started to go horizontal, so around 4.5. And then the stress applied to the system was, so taking a look at your reaction, so going back up here for one moment, energy is on the right hand side. So if we're looking that your reactants are decreasing and your products are decreasing and your reactants are increasing, it means we're shifting to the left. So to make that happen, it had to have been a decrease in temperature. Okay, so we're almost done here. This next one that we're looking at is asking, again, we don't see the question, so I guess we'll just skip that one. So sorry about that. And then we have one that is asked what solutions can act like a buffer. So to be a buffer, you have to be weak. So we can take out anything that is strong. And then to be a buffer, you're a difference of 1 hydrogen. So looking at what's happening within here, I would just have to see which one of these. I believe this one is the weak one. I just didn't have my data booklet. I was relying on my key. And I don't think I have this one. So that one is what I would go with. And then this last one, if you're asking about when the weak acids numbered are from strongest conjugate base to the acid with the weakest conjugate base. So strongest conjugate base would mean the weakest acid. So you would be going from your weakest acid to your strongest acid. That's how you'd want to order it, because that would have the strong, oh, wait a minute. That was right. That would have the strongest base to the weakest. So in order, if it was the data booklet, your strongest acids are first, and then they go down, making the weaker acids. So paired with the weak acid is a stronger base, because as you get up, the bases get weaker. So that was what we would want to look at from that order. So if you made it this far with me, I apologize for the questions that didn't work. If you did find this helpful, please subscribe. And if there's any other video I can do for you, just let me know. If you are writing a diploma soon, good luck on that. And thank you for watching.